All right, hi guys, welcome to topic 8 in the A-level computer science curriculum, which is databases. Now we basically got 3 sections that we're going to be going through. The first is just going to be an introduction to database concepts, and then we're going to look at some other topics that get further into the topic of databases and specifically how to manipulate them. So let's take a look at database concepts. Now in this section we're going to talk about what a database is, their structure, etc. So basically a database is a collection of data connected to a specific topic. And in computer programs, we often use databases so that when we close our program, we don't lose all the data that we've entered to that program. So if you just store data in like an array or a map or any sort of data structure that's in that program, then that's stored in memory. So as soon as you close that program, it's gone. Databases allow us to keep data consistently even when we close programs, because a database is going to be stored in the hard drive. It's stored in the secondary storage, which means it's persistent. So also when we turn off our computer, we're not going to lose it. Basically, a database is a way to store data. It's a method to store data. It allows us to retrieve and submit data, retrieve, store, and update data in a very fast and efficient way. And it's basically made up of tables. So we're going to be storing data in different tables, which are often related to each other in some way. When we talk about tables, you can think of, for example, an Excel spreadsheet. Now, each database is created and managed by a piece of software called a database management system, or a DBMS. And these are typically what we're going to be working with when we want to add data, update data, or delete data from our database. And there are a variety of DBMSs, so there are a variety of ways to manage databases, including SQLite, MySQL, PostgreSQL, etc. And oftentimes these can correspond to slightly different database structures. So each of these are going to have their own sort of pluses and minuses, or advantages and disadvantages. Now, in order to actually work with databases, to store data, retrieve data, delete data, edit data, we're going to use something called queries. And a query is basically you can think of it as a line of code, it's a line of text that gives the database specific instructions on what to do. And particularly when we're working with the A-level content, we're going to be focusing on a query language called SQL, or the structured query language. So we're going to learn how to write commands to do all sorts of things with our database in SQL. Now, why use database? We kind of talked about this initially, so it basically enables the processing and querying of data in a more efficient way than just storing something in a text file, for example. So this may not seem that important, but if we have, for example, 10 million medical records, right? Then using a database becomes a lot more efficient and a lot easier, especially if we want to find one individual record. Then, for example, in a text file, trying to go through every single line of text and figure out which one matches our criteria. Furthermore, we can generate reports and search information in specific formats. So we can create queries, or we can create criteria. We can create very complex criteria to get exactly the data that we want. And this is something that's more easily done in databases than text files or other methods. We have automatic support for data validation and verification when filling in a database. So in each table, we can specify what data is required and in what format it has to be in. And if we don't submit data in that format, or we don't submit certain types of data, we automatically will get a response that says, hey, you did this wrong. Database systems are standardized. So if we create a database with data, we can input and edit that data from multiple different programs and from multiple different computer systems. We can edit it using SQL, which is a standardized language, and generally, like, our database is something that can be utilized from different systems. And finally, especially depending on the type of the database, well, this is generally going to be true for any database, but databases give us the ability to store a greater amount of records than in a spreadsheet. And this also allows us to store it in a more secure way, such that the data doesn't get corrupted. So the data is separate from each other, every single record of data is separate from each other, and we can access it quite efficiently. And this is a big advantage of databases over spreadsheets. Just, we can store a much larger number of records in a secure fashion, and we can retrieve those records and make changes much more easily than in a spreadsheet, and much more quickly as well. Now, at the heart of databases are units called tables. And so if we're talking about a single database, we're going to have multiple tables in that database that each correspond to some topic or some theme of data. So for example, right here, if we wanted to store information on different castles in the UK, then we'd have a table like this. Now each table is going to have a record, and a record refers to each row of data. So in this table, we have 4 records. And each table is also going to have fields, and each of these represents a field. So status, location, construction date, and castle name. And if you kind of think about this in terms of a spreadsheet, each record is a row and each field is a column or a category of data. So in this table, we have four fields and 4 records. Now we'll often have different terms for fields and records, although those are kind of the standard terms. Now, each field can also be referred to as an attribute, so an attribute as a row, and that's something you might hear. Also, if these columns, so if this is an individual field right here, so if each of these is a field, then that means that this right here, castle name, is going to be a field name. Construction date, location, status are going to be a field name. So records, each record has different fields. We can also refer to the column as just a field, right? The castle name field. So now we know what tables literally are. Well, when talking about how data is represented in tables, then we need to use certain terminology. The first is an entity. And an entity is a real-world object or person represented by a row in a database table. So if we take a look at this example right here, our entity is a person because we're storing multiple people in the persons table. So when we're talking about an entity, we're not talking about an individual person. As a whole, we're talking about the concept that's being represented by each row in a database table. So if you go back to this example right here, we have different records, each representing an individual castle. So we can say the entity that we're representing is going to be a castle, right? Because each one of these rows represents a castle. That is the entity. It's basically the category of data that we're representing. That could be, or the type of data, I suppose. That's probably not the correct terminology, but probably to be more specific, the object, person, or I would say concept that we're representing by each row in a table. Now, if an entity represents the concept that's being represented by each row, then a tuple is an individual record that focuses on a specific instance of an identity. So if we're representing people in a table, then each row that represents an individual person, including their name, gender, age, and gender, is going to be a tuple. So right here, our entity is a castle. This is going to be a tuple, an individual record that is representing an instance of that entity. And the next concept we're going to look at is a primary key, and this is really the key to how databases work. Now, a primary key is a field that is distinctive for each record and is used to identify each record. So if you look at this customer ID, every single customer ID is different. And this means that if we were to ask the database for the row that has, for example, this customer identity, we can only get this row of information. So in that way, this is a key to getting the information that we want. And when we actually write commands, we write queries, and we're going to, if we want to find an individual record, we would actually just put the relevant primary key, which in this case is a customer ID, but can be all sorts of things. It doesn't have to be numerical. The main thing about a primary key is it has to be some string of characters that is unique for every single record in a table. And this shouldn't be called a database right here. This should actually just be called a table because right here we're just looking at a table. But anyways, so the main role of the primary key is to identify a specific record, and every single field for the primary key, so every single primary key right here needs to be unique, needs to be different from each other. So now that we have an understanding of how primary keys work, the next topic we can cover is foreign keys. Now, before we've only seen examples of single tables, but in general, when we're representing data for a computer program, we're probably going to have multiple tables, all representing different collections of information that are related to each other. So here's a great example. We have 2 tables. We have one that shows data for individual employees or stores data for individual employees. And we have one that stores data for individual departments. The reason I actually scratched these out are the original names because there was an error. They didn't make sense. Anyways, so if you look at our tables table, then we have 4 different employees. We have 4 records for 4 different employees, and each employee has an employee number. That employee number is going to be the primary key for this table because we could use that to identify each individual employee. So it's got a field for employee number, for the name of the employee, and then for the department number, right? But we want each table to carry information or to hold information that follows a specific category, that represents a specific category, which in this case is employees. This makes it easier for us to find information. Also, when we do get information from a table, we're not going to get information that we don't need. Because for example, if we're going to the employee table, we may only want information about an employee, not about the department. So there's not really any reason for us to get information about departments. Additionally, it might take longer and there might be more data involved. Moreover, if employees work for multiple employees work for the same department, then we're just going to have copies of the same information. Anyways, we have an employee number, employee name, and department number. However, each of these let's say that we want to find out information about a given department. We can use the department number with our department table because all the departments that are represented here in the department number field they all have a record in our departments table. So for example, right here, Sahil works for department number 101. We could take that department number, which is the primary key in our departments table, and we could go to 101 right here, and we could get the name of the department and its location. Similarly, if we want to find information for a tools department, which is 104, we could go to the department's table, we could go to record 104, and then we could get the information there. Now, employees uses primary keys from the department table. But the department numbers are not primary keys in the employee table. As I just said, they're primary keys in the departments table. In the employees table, because they represent a connection to a different table, we call them foreign keys. They represent a record in a foreign table in a different table. And foreign keys allow us to build relationships between tables. And the next concept we're going to cover is going to be secondary keys. This is actually kind of unrelated to foreign keys. It kind of goes back to primary keys. Maybe I should put it in a different order. But anyways, secondary keys are other keys in a database, or other keys in a table that are capable of functioning as a primary key. So if you look at this table right here, we have a primary key user ID. Every record has a unique user ID. However, also, if we could use the account number as a primary key, or we could use the email field as a primary key, because of the fact that every account number is different for every single person, and every email address is different for every single person that's represented in this table. However, we couldn't use names because, for example, we have names that can be the same. So secondary keys are basically other fields that could be used as a primary key, but they're not. Because when we do create a table, when we write our SQL code to create a table, we specify what the primary key is. It's also important to note that secondary keys could be called alternate keys. So just to kind of solidify our understanding of secondary keys and primary keys, let's take a look at a table comparing both of them. So here we have primary keys and secondary keys, and one similarity is that they both uniquely identify records. So we could use either the primary key or secondary to find a specific record in a table. However, primary keys can't be null. So there always has to be something in the primary key field, because that's how that's what we tell the database that we're going to use in order to identify individual records in a given table. However, secondary keys are kind of like alternates, so they can be null. They're not as important. Moreover, we can only have one primary key field at a time, but we can have multiple secondary key fields. That's not a problem. And the next type of key we're going to talk about is going to be a candidate key, and this is pretty simple. A candidate key is any key that can be used to identify a specific record on its own, so independent of any other field. And a candidate key is basically an amalgamation of two terms that we talked about before, a secondary key and a primary key. So if we're talking about a candidate key, we could be talking about either of these two, either a secondary key or a primary key. Now next, we have something that's slightly more complex, which is a composite primary key. Now, a composite primary key is not going to be an individual field, but it's going to be a combination of fields that we can use to identify a specific record. So we use this when we have a table, but one field is not enough to uniquely identify records. So for example, if we look at these two fields together, these function as our composite primary key. Now, separately, they wouldn't make good primary keys because we can have people with the same name and we can have people with the same birthdays. But the likelihood of having someone with the same name and the same birthday is quite low. So if we use both these together as a primary key, then that can be a way to uniquely identify a record. So then if we want to find a specific record in our table, we would make our query. We would ask the table not for just a name, but we'd ask for a record that matches both a specific name and a specific birthday. And that's the concept of a composite primary key. Now that we've covered keys and how to find things in a table, what I want to do is cover relationships, how different tables are related to each other. This will more closely involve the concept of foreign keys, which we really just talked about in one slide. Okay, so the first relationship we're going to talk about is going to be something called a one-to-one relationship. Now, here we have two tables. The first table is called countries, and the second table is called capitals. Now, what's important to understand is that we need to view this in the context of their entities. So every country has one capital. That's why this is a one-to-one relationship. We'll look at other examples, but generally, the two categories in a one-to-one relationship are going to have one of each other, right? Every country has one capital, every capital has one country, generally speaking. Now, another great example would be like if we were talking about like people and body parts. We could say every person has one nose, and then we'd have some data on their nose, which sounds weird, but that's actually like a logical example. Or we could say that every school has one principal, and then we have two tables with schools and principals. One table would have information about principals, the other would have information about the schools, and then they would have a one-to-one relationship. Now, when we actually get down to talking about tables themselves, the structures of tables that are related in a one-to-one relationship, we can see that actually they are linked by primary keys. So right here, for example, we have country, and our primary key is going to be country ID. So every country ID, it represents an individual record. Attached to that is a country name. Now, capitals are going to use the same primary key. So right here, where we have our primary key is country ID, and our second table for capitals, also, our primary key is going to be country ID, because this is going to be a unique identifier for each record. And additionally, every country ID represents every country, which is really just going to have one capital associated with it. And that can be represented by the capital name, along with any other data associated with that capital. So this is the basic structure of two tables in a one-to-one relationship. Really, you just need to understand the fact that they represent categories for which there's only one of the other thing. Every country has one capital. Every capital has one country. Now, let's look at a second example here. This example is probably something that is more likely to come up in an actual working program or a web application. Now, here we have a table of user data, and here we have user profiles, right? And think about something like Facebook. So every user is going to be represented by some data, so a username, an email, etc. And each one of those users is only going to have one profile associated with it. Now, in this case, if we look right here, our primary key on the user table is user ID. And we also have that user ID on our user profile table. And that could be used as a primary key for the user profile table as well. But we've chosen to use something called the profile ID. So the profile ID would probably be the primary key, and the user ID would be like a secondary key or an alternate key. Anyways, the point is, if we look at this relationship as a one-to-one relationship, every user has one user profile associated with it, and every user profile has one user associated with it. They're just different types of information associated with each. User's only going to have a username and email because it just represents a user. A user profile is going to have other information that represents what would go on the profile for that user, like a Facebook user, for example. That would be like a bio, maybe a birthday, their full name, which isn't really that relevant for the user itself, maybe an image, etc. Now, the next relationship we're going to look at is going to be a one-to-many relationship. And this means that for every record in one table, there are multiple records in another table that match up to that one record. So again, if we think about this in terms, like more conceptually, in terms of entities, every customer can have one or more orders. So each customer has many orders, one to many. And when we actually just break down these relationships, we kind of have to look at them from different sides. So for example, if we just look at this text right here, one to many, the one is right here and the many is right here, right? So the one is going to represent one table and the many is going to represent the other table. Now let's look at an example of how one to many would function in the context of an actual application. So right here we have two tables. We have a category table and we have a product table. Now a category table just represents a particular category of products. And a primary key on the category table is going to be category ID. So 1, 2, or 3, for example, some sort of integer with a category name attached to it. Now we can say that within every category, there are many products, right? Like we're not just going to have the category electronics with only one type of product. I mean, it's possible we could do that, but in general, we're going to have more than one. So if you kind of look at this right here, we have a primary key of product ID, but we also have a category ID column right here, a category ID field. And right here, we can see that in our category ID field that we have multiple categories that are used multiple times. So for example, the category ID 1, which is the electronics category, appears multiple times in our products table because there are many products that can correspond to that one category. Hence, it just makes sense that's the way it would be. And here, this is actually, if we think about this, this is actually going to function as a foreign key because this is going to act as a link to our category table. Anyways, that's just an example of how one-to-many relationships would work. One category, many products, and our tables are structured accordingly. Now, the last sort of relationship we're going to be looking at, I know this is like a bit fuzzy, but this is the best example that I could find, is a many-to-many relationship. Again, if you break this down, we're going to have many of one table that correspond to many in the other table. So here we have two tables. We have classes and we have students. And each class has the primary key class ID, and each student has the primary key student ID. But there can be multiple students in each class. So for example, if we have introduction to jazz, we could have many of these students that correspond to that class. Many of these students could also be in introduction to guitar. So we can have multiple classes that correspond. We can have one class that corresponds to multiple students, but we can also have multiple students that correspond to multiple classes. That's the nature of a many-to-many relationship. Many classes, many students. Now, if we look at a slightly more complex example, actually, this isn't really more complex. This is just a representation of how this would actually work in the context of databases, like structurally. So we have an author table here, and we have a book table right here, right? And we have primary key, author ID, right here that represents each individual author. And we have a primary key book ID that represents each book. Now, an author can be the author of multiple books in the book table. Additionally, a book could have multiple authors in the author table. So for example, both Emily Bronte and Charlotte Bronte could be the author for like one of these books right here. So we have a many-to-many relationship between the authors and the books. I'm sure you guys actually know who the authors of these books are. I'm sorry, I'm just like uneducated, and also like I just never liked reading like the classics. So yeah, I hated Jane Eyre. I said it. Anyways, so we have many authors that correspond to many books, right? And basically the way that we would structure this relationship in a database is we would have a separate field called the author book table. And this is going to act as sort of like, I don't want to say like a phone book, but it's basically going to represent a relationship between both of these tables, right? So first of all, in this author book table, we have an authorship ID that is the is the primary key for every record in this table, and basically represents every relationship. And every row is going to represent one relationship between an author and a book. right? So we can say right here that Emily Bronte wrote Wuthering Heights. I don't even actually know if that's true or not. Anyways, but right here, Emily Bronte apparently also wrote The Tenant of Wildfell Hall. So that's one author that wrote multiple books. However, we can also see right here that The Tenant of Wildfell Hall was apparently also authored by Charlotte Bronte and apparently by Annette Bronte and Anne Bronte as well. So the book also has multiple authors. And basically, this third table acts as sort of like an index that's connecting the authors in the books, because we can't really, there's no other way to represent this relationship just by using columns in either of these tables. This acts as sort of like a phone book is the wrong word. I like the word index, I don't know why. But it just basically holds the relationships between the author table and the book table. And there's a primary key right here, which I don't think we'd actually use very much, but every table needs to have a primary key. So that's why it's there. Okay, so to kind of solidify your understanding of these relationships, what I want to do is take a look at an A-level problem. So Bobby has a shop that sells products to customers. His database will store data about his customers, their payment details, orders, and the products he sells. Customers will have login details to access their accounts, and the database will update customers' payment and login details without keeping any historical records. So give one example of each of the following relationships from Bobby's database. So first is one-to-one. Then we've got one-to-many and many-to-many. So starting with one-to-one, we want to think of what every customer is going to have one of. And we've got a few pieces of data here that we can take a look at. So we're going to have customers. We're going to have data about his customers, their payment details, any orders, and any products he sells. So it also says here the database will update the customer's payment and login details without keeping any historical records. And this is actually pretty key because this means that we're not going to have multiple records of payment and login associated with each customer. So I guess an example of a one-to-one relationship could be the customer and payment details, because you're really just not going to have more than one of those according to the rules. Now next, one-to-many. So I guess every customer is going to have a certain number of orders, or there's going to be orders that are associated with each customer. So I guess it kind of makes sense that we could have many orders for one customer. I don't actually see anything else here that we would use. The products he sells, like we're not really going to have we wouldn't logically have a connection between customers and the products he sells, because any interaction with the products would just result in an order, right? So I'd say customers and products, and orders. And then many-to-many, probably orders and products, just because you could have one order, I suppose, with multiple products in it. So yeah, so I think probably orders and products. So you could have multiple products in each order. Each order could have multiple products. One product could be in multiple orders. That kind of makes sense. And let's see whether I was right. And yeah, customer to payment details or login details, because those aren't historically updated. Customer to order and order to product. Or I suppose customer to product. I didn't really foresee that relationship. That one's still weird. I guess that makes sense. But I kind of saw orders as more of being the sort of interface between customers and products. Anyways, that's kind of how we'd break down a problem involving relationships on the A-level exam. Now, the next concept I want to talk about is referential integrity. Now, this is a feature of relational databases, and it's the idea that every row has an identifier, or a primary key. Basically, it requires that every value in a foreign key column will be found in the primary key of the table from which it originated. So basically what it's saying is that if we have a student table, and each student is in a department, this means that every single one, basically what this means is that right here, this is going to be our foreign key column. So if students and departments, every student has a department attached to it, or that it's in, or that person is in. Basically, the idea behind referential integrity is that every department ID that exists in our student table should have a department in the department table. And this actually fails referential integrity because right here we have a department ID that doesn't exist in the department table. So this is the foreign key right here, and this is the primary key column right here. And this fails because we have a foreign key that doesn't exist as a primary key in the target table. And basically the idea behind this is that if this rule is followed, then the relations between tables are consistent. So we don't really have this like random foreign keys that don't correspond to anything in the table they're related to. Everything is consistent. Every foreign key has a matching primary key in the target table, which in this case is just the department table. And that's just the concept of referential integrity, which you need to understand. And the reason we're going over this right now is because we're going to start talking about normalization soon, which incorporates this concept. The next concept is indexes, or indices rather. Now, what an index basically does is it's a data structure that enhances the speed of data retrieval operations. And it allows us to basically find records in our database more quickly than if we were just looking at them one by one. So right here we have an index table. And basically what we can see is that we have, so in our index table, we have certain subjects, right? And the table itself is organized. So in this index, we have different disciplines. They're not just subjects, but they're disciplines, right? And this table is organized so that all the different disciplines are grouped together. So in our index, we have a pointer to where a certain discipline starts. So for example, right here, computer science, it points to this record because all the records, the next 3 records after this are computer science records, or correspond to the discipline of computer science. Similarly, right here, finance points to this row because this row and the next one after it corresponds to finance. And this way, what we can do is if we get a query, we see that the person or the record associated with that query has a discipline of finance, then we know exactly where to go. We don't have to look through all the records before in order to get to that particular record. Now, this is just a very simple example of how indices work, but basically it's just embodying, or it's demonstrating the idea that we have some sort of data structure that allows us to more quickly find individual records. So one of the downsides, or two of the downsides rather, that we have extra writes, meaning that we might need to write extra information to the database, and storing indices requires more storage space, so it's kind of a trade-off. But overall, query performance is improved, and we can locate information much more quickly because we don't have to scan the entire database. Now, generally speaking, when we are storing data, we have 2 options. We have the relational database approach and the file-based approach. Now, the file-based approach is basically when we store information like this. So we've got a folder, and we have that folder contains different folders. Within each folder is a certain text file or a certain type of data storage file that we would access if we want to get access to information. Now, what I will say is that the relational database approach is superior to this file-based approach, and there are a few reasons why. So the first reason is that the relational database approach reduces data redundancy because linked tables ensure each data item is stored only once. Now, in this approach right here, we could have the same piece of data scattered throughout. Like for example, in notes.txt right here, we could have some information that also exists right here in 2.txt. But in relational databases, we're only going to have any given piece of data stored once, and that can be located through links to other tables. Next, we can reduce program data dependency. And this basically means that we're not depending on any individual program to be able to write data to our data storage solution. So if we have the file-based approach, then our program needs to be able to understand where different files are located and store files in a specific format, and understand how to have a specific code to store information in that format. So you're going to have to write a lot of code in order to be able to correctly store information in a file-based system. But if we're using a relational database, all you need to do is you just need to have the address of the database, and then you can just execute a simple query to store information in that database, and also to get access to the structure of that database. Everything is centralized and much more easy to access, and generally you don't need to have specific blocks of code or different code in order to be able to access or store information. Next, we reduce data inconsistency, and that corresponds to this right here. With a single update, we can automatically reflect information in multiple tables. Also, it's easier to run complex queries if you want to get a very specific piece of information. Because of the way a database is organized, It's a lot simpler than trying to go through this file tree and get a piece of data from here, get a piece of data from here, access something here. It's just a lot more efficient and easy to use. So because we have linked tables, which means data isn't stored twice, because changes in data don't require us to rewrite software. So again, if the structure of this file system changes, we need to rewrite our software, which is not something that's true of the database. And just generally because of being able to update a database with a piece of information or multiple tables in a database with a single query, and really utilize more complex queries to get specific pieces of information or update very specific pieces of information, we can say that relational databases are superior to file-based approaches. Now in this section, what I want to look at is entity relationship diagrams. So basically entity relationship diagrams are ways of showing the relationships between entities in our table or in our database. If you remember before, an entity is basically the concept that's being represented by a table. And the whole idea of being able to visually connect entities and different elements that are stored in a database falls under the umbrella of data modeling. So what is data modeling? It is the process of creating a visual representation of a whole or part of information system, and it allows all stakeholders in a program or a business that's using a database to have a shared understanding of a system. So the idea is that whoever is involved with this database or this data stored solution can look at some kind of diagram and understand how all the information in that database is related to each other. Generally, any data modeling solution, like an entity relationship diagram, is going to show the type of data used, the relationships between those types of data, how data is grouped or organized in tables, for example, and data attributes, so different fields. Now, some of the advantages of data modeling are helping to avoid issues like redundancy, and redundancy means having the same piece of data or information in two different places. Maintaining the integrity of the database, which is a concept we'll actually get into later, and preventing a lack of consistency. So making sure that the relevant data, whenever an update is made to a database, that update is made wherever that data is being accessed or wherever that data has a relationship throughout the whole database. And this allows developers to develop a database in a structurally sound way. And this can be really important when you have a database with dozens or hundreds of tables. Now, getting down to what an actual ERD, or an entity relationship diagram, is, it's basically a diagram that allows us to illustrate relationships like one-to-one, one-to-many, or many-to-many in the context of a database. So if you look at this ERD diagram, we can say that license has an individual. So for every license, there's one individual, and an individual can have many vehicles. And license, individual, and vehicle would all be tables in the database. We don't necessarily need this text, but we need these lines. So this line right here, the single line between these rectangles, illustrates a one-to-one relationship. And this line with multiple lines branching off of it illustrates a one-to-many relationship. Okay, so now that we have an understanding of how ERDs work, or entity relationship diagrams, let's take a look at some A-level questions. So in the first here, the company uses a database courses to store data about courses and their tutors. These are sort of the primary entities that we're talking about. Each course starts at different times of the year and may have a different tutor. And right here we have the database structure. Now if you look at the structure, we want to make sure and pay attention to the primary keys, which are course ID, tutor ID, and in the case of course schedule, course ID. Now, one interesting thing, this is actually like a trickier question than you might think. So the tutor is not directly connected to the course information because there are many tutors that can correspond to a particular course. And also, tutors could teach different courses, and this is something you kind of have to infer. So in a way, like tutors and course information actually have a many-to-many relationship. But we need to show the relationship between all three of these tables. We can't just focus on course information and tutor. But if we look at course schedule, we have something interesting going on. So we have course ID and we have tutor ID for every single record in course schedule. So in a way, this course schedule table is kind of functioning like that third many-to-many table we saw in a previous example, with the exception that there's actually another primary key. So I guess together these would be a composite primary key. And so we have course ID and date started. So what we can do is we can say that for one tutor could correspond to many different course schedules, right? And equally, one course could correspond to many different course schedules, because we could have a single course. So if a course can have different tutors, then depending on when they start, we could have a single course with one tutor in January, one tutor in February, etc. So course information can also have many different course schedules attached to them. And there's no common field between course information and tutor, so we're not going to have a line between those. Anyways, the mark schema confirms that and basically says there's a one-to-many relationship as follows. Let's look at our next question right here. It says a shop manager has designed a relational database to store customer orders. The database will have the following tables, and we've got 5 different tables right here. Complete the entity relationship diagram for the relational database. So first off, we want to kind of want to look at these and understand how these are related to each other logically, and then what columns or what keys they might share. So we have customer, we have a shop order, we have supplier, we have item, and we have order item. And it looks like order item is related to item. So probably we'd have many orders that can correspond to one item. And yes, we have a composite key of like item order and order number there. Supplier ID is actually connected to supplier. So items connected to supplier. We have supplier ID that corresponds to a specific supplier. And shop order is going to be connected to a customer via customer ID. And there's no other real relationships that I can see. So let's start with customer. So it looks like a customer could have many different shop orders. So one customer could have different shop orders with different order dates. So we're going to have a one-to-many right there. And it looks like the item could have, okay, so we have shop order. So I think that relationship is kind of intact. Next I want to look at supplier and item. So it looks like every item is going to correspond to a supplier, but a supplier could presumably have multiple different items. So we're going to have a one-to-many right here. Like I don't see why a supplier would only supply one item. And then we have item and order item. And it seems pretty logical that, especially since they're 2 primary keys, that we could have multiple instances of the same item in that table. So we can have an item could correspond to many different order items. So also interestingly, we have one thing I missed. We have the order number right here and the order number right here. We'll get to that in a second. But an item can correspond to many different order items, and shop order and order item. So the relationship between those. So first of all, there's not really going to be any direct relationship between the customer and supplier. That much is clear. So we've got a shop order, and here we can have an order number. We have an order item, and we have an order number there as well. So we're basically linking up an order item with a shop order. So if those are both surrounding this concept of an order, then I think it kind of only makes sense that there'd be one shop order for one order item. Because we don't have because we can't have multiple, well, I guess we could have multiple orders right here actually. So, okay, we could have different order numbers for the same customer. And so I guess each of those could correspond to a different item, because that would be distinguished by the item number. Yeah, and so the idea that we could have different order items, so we could have the same order number, but we could have different item numbers, means that we could have multiple items in the same shop order, which means that we're going to have a one-to-many relationship right here. Let's go check the mark scheme. And yeah, I think we're pretty much correct. So we've got one-to-manys pretty much everywhere. Then we have a one-to-many right here. This one was actually kind of difficult for me to figure out, but again, as I said, right here we have this combination of item number and order number. So for one shop order, we could have multiple different item numbers, which means that we would still have a one-to-many relationship right there. Anyways, let's move on to the next question. A photographer creates a relational database to store data about photographs taken at birthday parties. The database photograph stores details of the customer, party and photographs taken, and the camera used. Photographer has several cameras that are used for taking photographs at the parties. Each camera has a specific lens type and a lighting type. Data about each photograph is stored in the database, including the party at which it was taken, the time it was taken, and the camera used. So again, let's kind of break this down. We have 4 different tables. We're going to have customer, party, photo data, and camera data. And so this photo data is going to have a camera ID associated with it. So we're going to have multiple photos, and each photo is going to be associated with one of those cameras. With the party ID, so it looks like the customer and the party are going to be quite closely related because we have a customer ID right here, customer ID here. But it does seem like a party, there could be multiple different parties with the same customer. Like, that's not an issue at all. So, okay, so first of all, one customer can have many parties. I think that just makes sense. And next, so if we think about, we could have different photos with the same camera. So I think one camera could have many different photos. So if camera data could be connected to many different photos. And also if you look at, we want to see the connection between the party and the family, and between the party and the photo. So right here we have our photo ID, we have a party ID. And one party could have many different photos, so I think it kind of makes sense that we'd have something like this. And are there any other connections? Let's see, customer to lens type and lighting type doesn't really have a specific connection to photo per se. Time taken, that looks like it's about it. Okay, yeah, and we're pretty much right. That's how it works. So now let's talk about the concept of normalization, which kind of draws together some of the different concepts we've gone over so far. Basically, with normalization, we take larger tables and we divide them into smaller tables in order to ensure data integrity and to reduce data redundancy. We're talking about data integrity. This includes a number of different qualities, including data consistency, which means that all the data in the different tables match each other. And it also means that things are set up so that relationships are pretty much staying the same, and when we update something, it gets updated in the rest of the tables accurately. Basically, it's the idea that the data is in the structure we want it to be and gets updated uniformly correctly throughout our operations of the database. And data redundancy basically just means that we're not repeating anything in the database. So every record represents a unique piece of information. And through normalization, we basically want to eliminate attributes with multiple values. So fields that contain multiple values. Do we have an example right here? So this is actually probably a great example where we have like a table within a table. Basically, there's multiple pieces of information here. We want to remove attributes that are repeated or that contain the same data. So again, I'm looking for an example right here. This is actually normalized, so I wouldn't find anything right here. But I'll show you an example, probably in a different table. That's something that exists. Basically, it's the idea that we have the same field repeated multiple times, maybe for the same record. Attributes that don't really describe anything, that just describe information that's not important to, for example, an employee. And I guess an example of that could probably be children, because it really, if the name of the table is employee, it really shouldn't be important like how many children they have. And this kind of relates to this one, but it's attributes with redundant information, attributes that are repeating the same piece of information over again. So again, I don't really see that so much here, but we'll probably see examples later on where that's the case. Now, again, we use normalization to reduce data redundancy, and this is to minimize the amount of data stored space, to reduce the table complexity. So for example, if we have a table like this where we kind of have tables within tables, like nested tables, and things are super complex, it can make updating, retrieving, deleting, or even simply adding new information a lot more difficult and more error prone. And also, we just want to make sure data is stored logically. So for example, an employee has certain fields, a sector has certain fields right here, a manager has certain fields. Things just need to make sense. Otherwise, it's going to make it more difficult for someone else to understand our tables or our database and to write queries appropriately. So now when it comes to normalization, one thing we need to learn is that there are different standards of normalization. So there are basically 3 forms of normalization that we need to learn, with the first being the least stringent, and the third being the most stringent. However, they do depend on each other, and we'll see why in a second. So basically, in the first normal form, you want to eliminate duplicate columns, so columns with duplicate information, and columns with multiple types of values. So for example, columns like this one that just have literally a table inside them or just have different pieces of information. Now next, each field should be atomic. So this basically means that fields should not have multiple types of information. So for example, if we have a field with name and there's a first name and last name, we should split those up. So instead of just having a name field, we have a first name field and a last name field. Now next is second normal form. And this basically means that we need to have all the characteristics of first normal form, but also create separate tables for each group of related data, each with unique primary keys. And all the fields need to be fully dependent on the primary keys. So if we go back to this example right here, we took this like massive messy table. And for example, we took something like children and turned that into its own table because that represents a different theme that's related to employees, but not exactly the same thing. We also created tables for job history and salary history. So these are all related to the employee, but they represent sort of different themes of data, so they don't necessarily need or should be in the same table. In the employee table, we'd only have the name and birth date. And one thing they don't show in these tables is that there would be foreign keys that would connect us to these tables. But regardless, this information is going to be in different tables: job history, salary history, and children. And that's what we need to accomplish in the second normal form. In the third normal form, we need to make sure there are no partial dependencies. And this actually mainly relates to when we have composite keys, composite primary keys. And we need to make sure that there's no fields that depend on only one primary key in that composite mixture, but not both of them. So to kind of understand all of these rules, let's go ahead and take a look at some A-level questions. So firstly, the following database table is not normalized. Explain how to modify the table to put it into first normal form. So just looking at this table immediately, we can see that student name right here could be turned into two different fields for first name and last name. That's kind of low-hanging fruit. So we need to make it atomic student name. And there's probably a better way to write this, but we'll see what that is in the mark scheme. Now, date of birth looks all right, tutor group looks all right. But here we have subject and we have subject code. So first of all, the first thing we need to do is this has multiple pieces of information right here: English, maths, and computer science. So we would need to split this up into different rows for each subject. So one row with just English, with math, and with computer science. So we'd have to split up the subjects. But also one thing I do see is we have a certain amount of redundancy. Like here we have subject code and we have subject, and EN just matches English, and MA just matches math, and CS just matches computer science. So we could get rid of subject code. I guess it kind of depends on how we're using the database. Maybe things aren't that intuitive, but that's probably something we could do. But either way, I'm just going to stick with these two for right now, particularly since this is only for 4 points. So yeah, if you look at the mark scheme, we have 1 point for each bullet point. So first of all, we can identify repeating groups of attributes in subject and subject code. So by that, we're just talking about the fact that we have multiple subjects in each field. And then we ensure that each field is atomic. That's another one we could do. And that just means that we need to split up the two. So this mark scheme is kind of mixed up, but the idea is you need to identify the problem and then show how you modify it. Right here it just says identify the primary key for the table, which, I think probably you'd be best. We could probably, I guess that is a problem. There's not really a primary key. I suppose like a combination of student name and date of birth could be the primary key, but also they didn't really specify how we should indicate what the primary key is. But probably we'd have a composite primary key of student name and date of birth. So I suppose that's just worth mentioning. All this mark scheme is really messed up. Anyways, regardless of the mark scheme, I think you kind of get an idea of how first normal form and normalization would work. So let's look at another problem. So it says the car rental database is not normalized. The current database design is this right here. Write a normalized database design for this database. use the field names, and underline primary keys. So right here, we're actually going to probably split this up into different tables and decide how it's normalized. So, okay, write a normalized database design. So let's go ahead and look at this. So first of all, for a booking, we do have a car registration, a car model, and a car color. So I think probably what we want to do is create a separate table for a car. And with booking, what I would really just want to do is I just want to have, so start date, end date, and then, I don't know, I have a big problem with the customer first name because honestly, that's not really a great primary key. So probably what I'd want to do is just add a customer ID. So we're going to change this in the customer table, but I'd want a customer ID and then I'd want a car ID. And that takes me to our customer. Well, okay, I'm going to create the car table now. And the car would probably just have like a car ID, a car registration, although I suppose the car registration could also be the primary key. But it's okay if we have more than one primary key. Car model and car color. I mean, I just indicated the car registration because I don't really know exactly like what is in that registration, whether it's unique or not. Okay, and now we have customer. And okay, customer first name, customer last name. I think all of that's okay, but I want to add a primary key because the first name and last name together even may not necessarily be a good primary key. So I'm going to have someone actually underline this as our car ID. And actually, one thing I want to do right here, I want to add a booking ID because that's something we don't have so far. And that's probably going to be our primary key. I kind of forgot about that. And then customer. So I would like a customer ID. And then obviously I want to keep the customer first name and last name. Customer last name. Email address. Hold on, I'm just going to go ahead and erase that right here. Customer last name. And then email address and phone number. I mean, we could use the email address and phone number as a like composite primary key, or even probably the email address as a primary key. But honestly, it's kind of messy. Like, I don't really want to use email addresses to identify customers. I don't know. It for me, like, it doesn't. Like if you have a primary key ID, I want something that is unique and that specifically is used to identify a customer. Email address and telephone address isn't really fulfill that purpose. It's really just more to contact the customer. So I not only want to be like technically correct, but also thematically correct, right? So okay. And all right, I think we're pretty much. So we have car registration, customer ID. So one interesting thing right here is that the car used the car registration as the primary key. But like, I don't really see why, like, to be honest, they wouldn't count it wrong if you also had a car ID because there isn't really any information given about the car registration. We don't know whether that's unique or not. Anyways, I think everything else is pretty much the same. We did add a booking ID primary key and a customer ID primary key, which is connected to our booking table. I think the only thing we did different was with the car registration, but again, I already explained that. And that's kind of how that normalization process would work. So now let's take a look at our next question, which is not so difficult, but honestly kind of tricky. So right here, a relational database garden has the following tables, owner and tree. The database is not in third normal form. Explain how the database can be normalized. So you've got owner and tree, and one thing that we do need to pick up on is the fact that every owner can have multiple trees, and every tree could belong to multiple owners. Like, trees are more of a common thing. They're not really going to belong to a single owner. And I know it's maybe not the most intuitive, but it's just something that we need to understand. So that being said, if we have multiple owners, multiple trees, then we're going to need to make some changes. But first, even before that, if we look at the owner table right here, we can kind of look at some of the fields, owner ID, first name, telephone number, all of these work. And we could have a tree ID as well, but the tree position definitely does not work. So that tree position would have to go right here to tree ID, and we could keep the tree ID, but there's also a few other things that we're going to need to do. One thing we can also notice when we look at the tree is the fact that for each tree, we have some scientific data, right? So you have scientific name, max height, and fast growing. And this doesn't necessarily apply to only one tree. We can have multiple trees of the same type as well. So what I would do is, first of all, I would create owner, right? And that's gonna have owner ID, and that's gonna have first name and telephone number. And probably we're gonna have, I think that, especially given the fact that an owner can have multiple tree IDs, it doesn't really make sense to have the tree ID right there. But what we're gonna have is we're just gonna have a tree table, and we're gonna have tree ID. We're gonna have owner ID. So it's gonna kind of link each tree with a specific owner and allow us to have different combinations of tree IDs and owner IDs. And then we can also have like a tree species ID, which means we're gonna have another table. It's gonna be like tree species. And in that, what we would do is we would say tree species ID, and then we'd have information that corresponds to a specific tree species. So scientific name, max height, and fast growing. Because again, this is just information that would be replicated. Like we would just be copying the same information over and over again for different trees. So if we just have one record in a tree species database that we're going to reference right here, then we're not going to be copying as much information. So tree species ID, and in that we're going to have scientific name, max height, and we're going to have fast growing. So this is two things. So first of all, we kind of have this tree table right here, which functions as like kind of another table that allows us to have a many-to-many relationship between the owner and the tree. Because like we can have different trees that we can have different combinations of tree IDs and owner IDs. And this could function as like a primary key. Right here, owner ID is going to be a primary key. Right here, tree species ID is going to be a primary key. And also we're preventing the replication of data by separating this stuff right here that could apply to, or this information that could apply to multiple different trees that are of the same species. And okay, if you look at the mark scheme, like it says removing the many-to-many relationship, move tree position into tree table. Did I actually do that? No, actually that should actually be right here in tree species as well, or tree position, because that's gonna correspond to an individual tree. Put owner ID into the tree table, which we did. Create a new table with a suitable name for the species. And you could have the scientific name as a primary key or another suitable primary key. And I just used the tree species ID. I guess scientific names are unique, so it would work. I just didn't think of doing that. Now the next topic I want to talk about, which I think should make sense by this point, is the idea of a logical schema. And especially in 3NF, what we try to do is we try to have multiple logical tables that are connected to each other. And by logical, that means each one represents a specific topic. So for example, we had tree, owner, and tree species. That allowed us to prevent the replication of data, but also it was kind of logical. So right here, for example, we'd have students, courses, and enrollments. And this is a term you need to know, but the bottom line is it basically means organizing our database into tables that make sense. That's opposed to an illogical schema, which has redundancies, poor structure, and a lack of normalization. So here we have student ID, we have course information, and we have an instructor. Well, I suppose the instructor could be there, but we have student and course information all in the same table, which is kind of replicating information, and it just doesn't really make sense. Anyways, now we're going to move on to database management systems, and we're going to look more into how to technically interact with a database. Okay, so the first concept we're going to talk about is a database management system, which is something we touched on before, but essentially a database management system is a set of programs or one program with several components that allow an application, a user, or another database management system to read, store, change, or extract data from a database. So essentially, a database management system is a set of programs that allow changes to be programmatically made to a database. For example, if we're typing some sort of commands in SQL or whatnot, then that's going to be executed in a database management system. Or if we write a program that's going to store data in a database, that's all going to go through a DBMS. It's basically the interface for a database, for any type of database. Some examples of database management systems are SQLite, MySQL, PostgreSQL, etc. And if you've done any sort of application development, you've probably heard of these. Now, in a database management system, there are several crucial components that we need to learn about. First is a data dictionary. And the data dictionary is responsible for managing metadata, and metadata is essentially information about how the database is structured. So this includes all the tables in the database and the fields in those tables, as well as things like data types, length, whether those fields are acquired or not, etc. So basically what a data dictionary does is it includes data not about what's in the tables or not about what's in the database, but about how the database in general is structured. Now next is a data safety component. So in a DBMS, there's going to be a program that allows for the backup and recovery of the database, and also make sure that data integrity is maintained, so that data is being stored appropriately so that it won't get corrupted or lost. Next, we have a query processor, and a query processor accepts and interprets queries in SQL and returns the appropriate output. So this is what allows us to, either through programs or just by interacting directly with the DBMS, make changes to the database via a command-based language, which is SQL. Next, we have a storage engine, and the storage engine actually handles the create, read, update, or delete operations in a database. Now, the query processor may parse whatever queries we submit to that database, what are queries being those commands, those text commands. The storage engine is going to actually be the one that makes the changes. Next, we may have some component that helps us handle concurrency. So it allows multiple users to access the database concurrently at the same time and then make changes. And this aspect of the DBMS will make sure that multiple users are not trying to modify the same piece of data at the same time. And finally, we would have a security component to the DBMS, and this enforces user access policies. So this basically only allows certain users that are created as part of the database to make certain types of changes, essentially allowing or essentially enforcing who can make what types of changes to the database. Now, as part of a DBMS, we have something called a developer interface. And this is a way for developers to directly interact with the database. And this can come in a few different forms. The first can just be command line tools or graphical user interfaces. We can also have APIs, which are essentially packages of code that we can use in order to make changes to the database. And right here is an example of a developer interface, and this is just a command line tool that pretty much comes with a lot of different SQL-based systems or SQL-based database management systems. Right here, we're just creating a user, and basically we can type commands to make changes to the database. And it's through these types of tools that developers can allow their programs or can personally make changes to a database. Now, one important role of database management systems is security, and database management systems can enforce security through several different ways. The first is access rights, so creating a set of users and basically controlling which users can read, write, and make any other changes to a database. Next is an audit trail, so we'd record any changes to the database. So if some change is made that may be malicious in some way, then we know who made it. Data locking a row is currently being accessed. And basically, if we lock a row that's currently being accessed, then we can make sure that no other record is going to try to make changes to it at the same time, and so they don't get jammed up and create all sorts of problems. Validation is a part of this role, making sure that new data submitted to a particular database or a specific table follows the necessary rules for that table. We can enforce encryption, so we can encrypt data in a database. So if someone tries to access it without certain credentials, they may not be able to access any of the data in the database. And finally, DBMSs allow us to back up the information in the database, continually updating that backup version. Now, as we said, one other function of DBMSs is in enforcing data integrity, and we touched on this concept earlier, but I just want to come back to it because it is quite an important concept in understanding what DBMSs do and in general how data ought to be maintained in a database. So there are basically three important things that are part of data integrity. The first is accuracy. So the fact that the correct data and relationships are retained and preserved in a database. Relationships being really key. Next is completeness. So no data has been lost or is able to be lost. Finally, validity. So any data in a particular table meets the predetermined rules for what that data is supposed to look like. So for example, it might have to be an integer, It might need to be Boolean, or it might need to be a certain length, etc. And some ways to preserve data integrity in general are to validate data, back up data, keep an audit trail, control who accesses it, make sure there's no duplicate data, and to validate any sort of input that's going into that database. So these are among some of the ways we can use to maintain data integrity, but I think it's just crucial to understand exactly what data integrity means. Now, one aspect of a DBMS, or the next aspect that we're really going to dive into, is called a data dictionary. Now, as I said, this contains metadata, but what that really means is that there's a file or set of files that stores information about the database and the tables inside of it. So at minimum, we're going to have the names and descriptions of tables, names of fields, data types and lengths of fields, and relationships between tables. So it's kind of the blueprint for what the database as a whole is going to look like. This is an example of what a data dictionary would look like. So if you look right here, we basically have for this table. So we have a table called just data, right? And we have the table itself with all the information in it. Then we have the data dictionary, or the part of the data dictionary that corresponds to that table. As you can see here, we have all the names of the fields, their data types, and some descriptions of what they represent. Now, this first section, we're going to focus on data definition language, which essentially consists of commands that allow us to define our database. More specifically, we can define and modify the structure and metadata of a database. And these commands are used to generate a data dictionary. And based on the data dictionary, we will create we'll structure our database. Commands that come under the umbrella of database definition language are part of the SQL language, but they're only available to database administrators, so people with the permissions to actually make changes to the database. All these right here are examples of some of the types of DDL commands that we'll be talking about. Now, the first is a command to create a database. Now, typically a command like this is going to be typed into the console or terminal like so after we log into our DBMS, so our database management system. And right here we have create database DB1. That's sort of how we would create a database. So we'd have create database in capital letters, and then we have the name of the database we want to create, followed by a semicolon. This is the basic syntax, and this is just an example. It's a pretty straightforward command, to be honest. One thing we might have to do before we can actually create a database, or one thing we might do once you create a database, is to give some users the access to that database itself, or to tables in that database. Now, what we can do once we create a database is we can actually create tables in a database. And we're going to do that using the create table command. So right here, if we want to create a table called contact info with 4 fields, we would do create table, contact info. Then we would have some parentheses. Inside those parentheses, we would have the tables where we'd have the fields in that table. So we have an SSN field, we have a name field, an email field, and a phone number field. And next to those, we have other characteristics. So we have the data type, so integer varchar, which basically means it's 50 characters, 100 characters, and 15 characters. So these are all essentially strings, but they're more defined. I mean, the way that they're referred to is just like lists of characters. And right here, we also define our primary key. So the SSN is an integer. It's going to be our primary key, and SSN stands for Social Security Number. If you're American, you know what that is. If not, then you don't. But the point is it can be used as a primary key because it's unique for everyone. Next, right here on name, we have the not null command, and this basically indicates that when we input a record into the contact info table, that field can't be null. It can't be null. So we need to have some kind of name. And this is the general syntax: create table, the name of the table, and then we have the names of different fields, followed by data types, and then different field settings. Now there's a variety of settings we can use. This is a very limited sort of collection, but you really just need to know, for example, not null. You don't need to know a ton of field settings. Now, another command we can run is the alter table command. And this is for us to add a field, or to modify a table that already exists. Now, there are different modifications we can make. In this case, we're just going to be focusing on adding a field. And so we have this table that we actually created, that we could have created using the previous example: SSN, name, email, phone number. Also, there's hours, which we didn't have before. but that's what we're going to add. So right here we have an example. We want to add the field hours. We're going to say alter table contacts add, and I should actually have hours inside there for the name. Add hours varchar 10. So we are going to have hours. We're going to add the hours field to this table, and it can only be 10 characters long. So it's going to be quite limited, and that's because we're either going to have it's either going to be part-time or full-time. There's really two options. The alter table contacts, right in here, we should have the name of the actual field we're going to add, and then you can have other field settings. We're going to have the data type, and then we could also have other field settings after that. Now, next, what we're going to do is, so we've created a table, and this is kind of weird. This is kind of a weird one because I did see this in the A-level curriculum. But what we're doing right here is we're taking, this kind of assumes that we've already created a table that doesn't have a primary key, which is not really possible. I think instead, maybe what happened is we added another, we added a new field called employee ID, and we want to make this the primary key. So if we want to add, or we want to, I guess, change the primary key really on a table, then we would do alter table employees. We'd run that command first. And right after that, we'd have add primary key, parentheses, and then the name of the field that's going to be our primary key field. So right now, this isn't considered a primary key, but after this command, alter table, add primary key, and then the name of this field in parentheses, that would make that the primary key. Now, next what we're going to do is we're going to add a foreign key, and we want to add a foreign key to link the context table to the employees table. So basically, just to add a foreign key, what we need to do first is add a foreign key field. So what we can do is we're going to do alter table, and then the name of our context table, and we're going to add employee ID integer. And this is actually more or less the same code we use right here for adding an hours field. Like the main difference is we have a different data type, really. So basically the first thing we need to do is add a new field to add a foreign key. What we can do is we can go ahead and populate that field with records, but we don't have to do that just yet if we don't want to. But we do need to do is specify the foreign key field on the employees table. So essentially we're making, well, actually on the context table. Well, yeah, on the context table. So essentially what we're doing is we're making two changes. First, we're just adding the field. And then we're actually specifying that this is a foreign key field. So there's some other code, longer code that's involved here that you should understand. But anyways, what we're doing is first line is alter table contacts. And whenever we just want to make a change to a table, it's going to be the first line. We have add constraint. And then we're going to give that constraint a name. It doesn't really matter what you call it. You can call it whatever you want. This just happens to be the name. FK underscore contacts employees. FK stands for foreign key. Contacts is a table that's going to have the foreign key, and employees is going to be the table that it links to. Then we're going to say foreign key employee ID, and this employee ID right here references what's on the contacts table. So this line is for the context table, and that's this field that we added right here. Then we're going to add the keyword references, and then we're going to have employees, which refers to the employees table that we're linking to, as well as the field in the employees table that we're going to be able to access, that we're connecting our context table to, based on the data in the employee ID field in our context table. So let's say we have in our context field, we have an employee ID of 1. Then this 1 is going to be the ID for a row in the employees table. And we're gonna check this ID against some field called employee ID in the employees table. So this could maybe, like, if we wanted, or maybe the employees table doesn't have an employee ID field, and instead it's just called person ID. It doesn't really matter what it's called, but right here, this employee ID in the context table, when we want to get information about that, like based on that employee ID, we're going to go to person ID, or we're going to go to whatever is specified here. Like that's the connection to the employees table. So this is actually pretty awesome. Right here we have an example. So this is an example this is the result from the code that we executed in our previous slide, or we showed in our previous slide. So right here we added an employee ID field, to our contacts table. And this is referencing the employee. So this is our employee table. And this right here is the foreign key. We'll just say FK. And that's referencing this field right here on the employee table. And that connection is being made in this block of code that we spent like quite a bit of time explaining right here. Now right here, we have an A-level example that I'd like to go over. So it says part of the database table bird type is shown. We have bird ID, name, and size. The database only supports these data types. Write a structured query language script to define the table bird type. So what we essentially want to do is we want to go ahead and create this particular table. And so we're going to do create table, and then bird type, parentheses, and first we have bird ID. So we're going to have bird ID, and then we're going to have the data type right after that. That's just going to be, I want to say it's an integer, I think. This is going to be an integer. And that's probably going to be the primary key, so I'm just going to write primary key right there. Sorry, I hate writing. And then name. And that's just going to be, it doesn't really specify. I would probably say it's just going to be like varchar. And then maybe let's just say like, I don't know, 20. And it's going to be comma, comma, and then size. Probably going to be like varchar 10. I don't know, it's not really like specified. And then we're just going to close that and we're going to have a semicolon. Okay, and right here we just have an example answer. So we're going to have the bird ID. Basically, like what we need to do is we need to have the bird ID as a char or varchar. And that's kind of weird to me, actually. I don't really know why that wouldn't just be, I guess maybe it's going to be an integer because we're not going to do any mathematical operations on it. It's just sort of a tag. So yeah, I mean, I guess that should probably be just varchar. Okay, that's fair enough. So yeah, it's just a tag. We're not planning on doing any mathematical operations on it. So probably that should just be a varchar. And I imagine that's just going to be like 4 characters. Okay, fair enough. But yeah, that's got to be the primary key. So bird ID is primary key. And this is like a different way to doing it. This works as well. What we did is fine as well. So you can specify that as part of the command, or you could actually just include it in when we're defining that particular field. Name and size is varchar, which we did, and that's pretty much it. Okay, so next example. It says example data from the table rental are given. Complete the following data definition language statement to define the table rental. So I think it should be pretty straightforward. So we're going to create table, and that's just going to be called rental. Sorry, I hate writing. And we have house ID, and I think house ID is probably going to be varchar again, because like we said, it's not, we're not doing, well, also there's letters, so varchar. Monthly cost. Okay, so this is actually a decimal. So this is actually going to be something called real. But if you go back here, we actually have like the types of databases we can use, and this is a decimal, so we're going to go ahead and use real for that. And deposit paid, boolean not null, and then, okay, rental ID. And okay, so that's going to be the primary key, and that's what we want to define here. So we can just use the same command that we actually saw right here. And primary key. Like, to be honest, you can define the primary key both ways, but just seeing as this occurs, so it's more common to be defined this way, I would probably just go ahead and make sure to define the primary key after you defined all the fields. So is that capital? Yeah, good. Okay, cool. And yep, that's another A-level question where we make use of DDL. And I think we're good to go. Interesting. Real, or we also have a currency data type that we could use because this is monthly cost. Now next, write the SQL. Okay, so next write the SQL script to add one field to the table photograph to store the resolution of the photograph. Okay, so for storing resolution, we're basically just storing this right here, 1920 by 1068. And so that's just going to be like a string of characters that we need to store. So what we can say is we can say alter, so we can say alter table photograph and then add Probably we just want to add resolution. Let's like add a resolution field. And that's just going to be varchar. Let's say probably, I don't know, let's just make that, I want to say like 12 maybe. We have 4 here and we have 4 here, which is 8. But we also have another space right here, another space right here. So we have 3 extra values. So maybe like 11. I don't think that really matters as long as we just have varchar. You really, what they're looking for is just a data type. And that should pretty much be it. Sorry, I spelled that wrong because, okay, cool. All right. And yeah, that's pretty much it. Alter table, photograph, add resolution. Also, we have a text data type, which is interesting. But varchar, 11, yeah, because the spaces do actually count. Spaces between this X right here. And on either side, we had 4 characters. So 4 characters on one side, plus 4 characters on the other side, for a total of 11 characters. So now let's move on to data management language and the commands that go with that. Now our next section is going to focus on something called DML, or data manipulation language, and this is an appropriate title because we're going to be focusing on not necessarily how to change or create a structure for databases, but how to alter the information that's already there. So at the core of DML, data manipulation language, is going to be select statements, and these are basically used to get some set of data from a table, or it can be from multiple tables based on certain criteria. So here's an example of a select statement. So let's say we have a table called customers. If we want to get all of the information in 2 fields in a table called customers, we do select product name, which is one field, comma, price, which is another field. And that would just output all the product names and prices side by side in the customers table. So let's look at an example that actually just matches with what we just saw. So here we have a table called products. And you can see we have a couple of different fields. We have product ID, product name, supplier ID, category ID, unit, so the unit in which these products are presumably being shipped, and price. Now, the first query we have is select product name from products. So if you execute that query, select product name from products, then that means we're going to get all the product names, so everything in this field in the table. And this is going to be our result. So basically, if we just do select and then a field name, we're going to get everything in that particular field. But again, in here, we're usually going to have some criteria, and from is going to be followed by the table that we're actually working with, because there can be multiple tables in a database. Now our next example is select product name and price, comma, price from products. So that means that we're going to get all of the product names and prices. And this is a table, so we're going to get matching information. So we're going to have the product name along with the corresponding price side by side, and that as a whole is going to be our output. So what would basically happen is in the console, we would open up our DBMS, or database management system. We would log in, we could type in a query like this, and then in our console, we would just get this displayed. We would just see the text that represents this. Now, that was pretty simple. We just got all the values in particular fields. So what we're going to do now is get some values according to criteria. The first criteria is going to be where price is greater than 20, focusing on this field right here. So if you look at this query right here, you have select, which is going to be the beginning of all of our data manipulation language statements. We have, so it says we have product name, which is the actual information that we want to get. We really just want to output product names. We have the name of the table after from, but then we have where. Now where is something new, and after where we're going to have some criteria. And our criteria is where price is greater than 20. So price is referring to this field right here, and any criteria we have are going to be relative to some field in the given table. So we're going to go ahead and look for all the prices that are greater than 20, and that's this one right here, and this one, oh sorry, those are less than 20, my bad. So greater than 20 is going to be this one right here, and this one right here. So we have the instances, we have the rows where the price is greater than 20, but we're not outputting the prices. We're actually just outputting the product name. So our output is going to be the product name that corresponds to the rows in which we have these prices. And it's going to be Chef Anton's Cajun Seasoning and Chef Anton's Gumbo Mix, and hence that's going to be our criteria. So here we are going to have our criteria, and here we're going to have the actual fields that are output. Now actually something that's important to cover that maybe I haven't covered so far is that we can output multiple fields using commas, but also if we just have a star here instead of any field, that means we're going to output the entire row, so every single field in the matching row. And actually we just have an example right here. So select star from products where supplier ID is, this means not equal to, so is not equal to 1. So that means we're going to go to our supplier ID field right here, and we're going to look for the rows where the supplier ID is not equal to 1. And that's row 4, or row product ID 4, and this row as well. So if we have, so that's our criteria, but we have select star, which means we're going to print out all of the fields from this matching row, all of the fields from this other matching row, and hence this is going to be our output. Now our next example is slightly more complicated. So here to select product ID and price from products. So that means our output is going to be some product ID and price from products where price is greater than or equal to 18 and price is less than 22 and unit like boxes. So we've got a bunch of criteria right here. What I want to focus on is these first two criteria. Okay. And I'm just going to circle the matching values in red. So price is greater than or equal to 18 and price is less than 22. It's basically going to include this value right here, this value right here, and this value right here. So these are all greater than or equal to 18 and less than 22. But also, we need to match unit like boxes. Now, when we use like, we're searching for some string within a collection of within a longer text. So we're not looking for a field in unit that is just boxes, but we're looking for something that contains the boxes, that contains the text boxes with some other text on either no text or some other text on either side. So boxes can either be in the middle of whatever text is already in unit, like right here, or it could also be at the end, like right here, where there's no text on this side. So basically boxes has to be somewhere in the text. And so based on this criteria, I think I'm gonna use a different color. I'm gonna use probably black. So we circled in red which rows match our first two criteria. And now we're gonna circle in black the ones that match all red, or the ones that match all of them. So it's gonna be this one right here and this one right here. Because for these particular rows, we have the word boxes in unit. And we also have the word boxes. Well, yeah, so we have the word boxes here and right here, but both these rows also match these criteria right here. It's actually kind of weird. So right here we have our product ID 5 as output. So we're going to output the product ID and the price. So we have product ID and price, but we should actually also have product ID 1 and price 18 for this particular row right here. We actually made a mistake, but now we fixed it. So this is the product ID and price for all products that fit all the criteria after where. So these two criteria, price is greater than or equal to 18 and price is less than 22, and the unit like boxes. Now one thing to keep in mind is if we had unit equal or with a double equal sign or a single equal sign I think as well, boxes, so like equal boxes, that means we would only be looking for a unit where we have boxes in here. That brings us to our next slide, comparing strings with like and the equal sign. So here we have two examples right down here with 36 boxes and one that's very similar to what we saw, or basically the same as what we saw before. So right here, if we have select product name from products where unit is equal to 36 boxes, we're literally looking for this exact string. So this is the only row that could match. And if we're doing select product name, that means we just want to print out the product name for this matching row, which is going to be Chef Anton's Gumbo Mix. Now next we have select product name from products where unit like boxes. So that means that, again, we can have something on either side, but we don't have to. The point is boxes is somewhere in the text for a given field in unit. And that does match this field right here, so this text right here, and this text right here. And we did select product name, so our two outputs are going to be Chase and Chef Anton's Gumbo Mix. Okay, so now we're going to look at a different kind of keyword. This is called the order by keyword. So right here, we're moving from just simply extracting specific information to extracting it and then putting in order. So right here, it says select product ID, product name. Basically, like we could have just put a star right here from products. And then after from products, instead of where, we have order by, price, descending. So order by, price in descending order. So if you look at what the result of that is, we're going to start from the highest and go down to the lowest. And so if we're going to order by price in descending order, we're starting at 22 and we're going down until the lowest value right here. So if you look at the syntax, everything's pretty much the same, table name, fields, but we're just ordering by a certain field, and we're ordering that in either descending or ascending order. And so partly again, because we got every field, this is what our result was by. What it was, we were just changing the orders of the rows based on the price field, and that being put in descending order. Now, more broadly, if you look at the order by keyword, so right here, we can have criteria. So we can basically use the where keyword with criteria, and then we can put the result in a certain order. So for example, right here, we have select product name from products, where supplier ID 1 equals order by product name ascending. And if you wonder what product name ascending could possibly mean, that's actually going to involve alphabetical order. So presumably we're going to start at the first letter in the alphabet and then move our way downwards. So if you actually look at an example right here, it says select product name from products where supplier ID equals 1, order by product name ASC. So the first thing we can look at is we have this criteria, supplier ID. So, and we're only looking at the rows that have a supplier ID of 1. So it's going to be this one, and this one. And then basically we're just going to output the product name. And we're going to output our result in order of product name in ascending order of product name. So we're starting with, so we have Chase, Chang, and aniseed syrup. We're going with aniseed syrup, Chase, and then Chang, because that's how things fall in alphabetical order. Now, also we could have instead of outputting product name, we could have just like output like product ID, but the product IDs would have come in order of the ascending product names. So for aniseed syrup, we would have gotten something like 3, 1, and 2. So basically that, so from the rows that are supplier ID of 1, the order of the product, the ascending order of the product name dictates whatever order our output is going to be in. So next we have sort of a similar order by statement, but we're going to select product name and supplier ID. So that's what we're going to output from products where price is greater than or equal to 19. So let's see which prices are greater than or equal to 19. Just circle these right here. And we're going to order those by price in descending order. So that means that if we were to order these in descending order, we would start with the highest value and then work our way down. So that means that the first one that we would see would be, so the first one would be this, the second one would be this, and the third one would be this. But we're just outputting product name and supplier ID. So first we'd have Chef Anton's Cajun Seasoning, and we would have supplier ID of 2. Then we'd have Chef Anton's Gumbo Mix and a supplier ID of 2, and then we'd have Chang and a supplier ID of 1. So we're essentially outputting the elements in the descending order of price, only for prices that are greater than or equal to 19. Now next we have a group by command. This basically allows us to group certain elements. So right here what we can do, I mean we have a bunch of different ways that we can use this. But so right here we have select category ID. So really we're going to output a category ID and then count product ID as total products from products group by category ID. Okay, so we're outputting category ID, but we are basically then going to have another column that we created called total products that doesn't exist. And we're going to count the number of times a given product ID is and it basically exists for that given category ID. So we have category IDs 1 and 2, right? And we can see that we have product IDs. So we have for category ID 1, we have 2 product IDs. For category ID 2, we have 3 product IDs. So we're basically just counting the numbers of product IDs that we have for each given category. And that's basically what the group by allows us to do. The group by is going to break us is going to give us categories. So we're going to output the category ID, but it's basically going to give us the distinct categories that exist, not just like 1, 1, 2, 2, 2, but just the distinct categories, distinct groups. And then based on that, we can calculate some total or some other characteristic. So here we actually have a slightly different scenario. So we're going to select supplier ID. So it means we're going to be outputting supplier ID, but we're going to count product ID as total products. So for each supplier ID, for supplier ID 1 and supplier ID 2, we're counting the number of times we have a product ID. Or the number of, sorry, not the number of times, but the number of product IDs that we do have. I should have specified that. I don't know if I just said basically the number of product IDs we do have, like in the previous example. I may have said something different, but that's how it works. And for supplier ID 1, we have 3 product IDs, and for supplier ID 2, we have 2 product IDs. And so that's going to be one column. And then we have a comma, and then we've got another column, which is the average price. The average price is going to apply to all of those with a supplier ID of 1. And you can see those with supplier ID of 2 tend to have higher prices, which is why the average is higher. And that's all coming from, we had this as because that's what the column is going to be named. Every time you have an as, that means we're taking some value, like a count or an average, and storing it in a column of a name we don't have yet. That we're just specifying like right here. And that's going to come from the products table, and then we have group by supplier ID. And this group by supplier ID is crucial because that means that we're going to make for supplier ID that we selected right up here. We're just going to be having 1, 2 instead of like 1, 1, 1, 2, 2, 2. So literally just going to be displaying the supplier ID as groups in terms of like what values are available rather than each individual value in the supplier ID column. Now that actually brings me to calculating a sum, which is something that we touched on. We actually touched on counting, so counting how many of these values match up to a given supplier ID, or counting an average. We haven't talked about sum yet. So let's look at the syntax. So similar to our average and our count, what we're actually doing is we have sum, we have parentheses, and then we have the values that we want to, we have the field whose values we want to add up. So if you have select sum price from products where category ID equals 2, that means that we're going to want to add up the sum of the price for all the values whose category ID is 2. So this one, and this one, basically we're going to be adding these together, and we basically get the result of that addition, of that sum. Similarly, right here, sum price from products where price is less than or equal to 22. That just means that we would be like, okay, where do we have a price of less than or equal to 22? That's actually pretty much all of them. So we're just going to be summing those up and just outputting them out. Now going back to our previous example, if we want to count how many records meet a certain criteria. So right here, we're going to count price. It basically means we're going to count, okay, so we're going to count price from products where category ID equals 2. So we have three category ID equals 2 values in our table. So this basically happens 3 times, and we can just basically count the number of prices we have. So that's just 3 prices, right? So we can count we can basically count how many instances that's happening. I mean, we could even count units, or we could count something else, but this basically just gives us a count from a given field. And this could actually be important because right here, we don't have any null values. But for example, if this was just null right here, if there's nothing here, then the value would be 2. So that's kind of why it makes sense to do that. Calculating average. Actually right here, this shouldn't be count price, but it should have average right here. Average parentheses. And for this one, price actually matters because we're calculating like a numerical average of values. So if you select the average price and parentheses price from products where category ID equals 2, that means we're just going to be worried about these rows. We're going to find the average of all these values. And the next major concept we're going to cover is going to be the concept of joins, and this is used to get matching information from 2 tables. and output it as a third table. So we're not actually going to create a new third table in our database, but we're going to output something that looks like a table. Now there are different types of joins, but the most common type of join we're going to work with is going to be the inner join, and this is also the only type of join command that's used on the A-level exam and the IB exam. This slide actually comes from a presentation I originally made for the IB exam. But as we'll see in the A-level practice questions we're going to cover soon, it basically works the same way. So what I want to do right here is show you two tables. First, we have a customers table and we have an orders table. In our customers table, we have two fields, the customer ID and the first name. And the customer ID is going to act as our primary key, with 1, 2, 3, 4, 5 being some of the fields, or some of the IDs that are in the customer ID field. In our orders table, we have an order ID as a primary key, an amount, and we have a foreign key right here for customers. And in here we have IDs that should match what's in the customers table, and specifically what's in the customer ID field. But we also have some IDs here that don't necessarily match. What we want to do is we want to find the IDs. We want to find the IDs that exist in the customers table, but also exist in the customer ID. Exist in the customers field right here, but also exist in the customer ID field. We want to find matching information for those particular fields. So if we go down to the result right here, we have a customer ID, and for each customer ID we have a first name, which comes from this field right here, and we have from this field and this table in the customers table, and we have an amount right here, which comes from the orders table. So basically what we were able to do is aggregate information from both tables that share a customer ID. That customer ID is shown in the customer ID field in the customers table, and in the customer field in the orders table. So right here we have the code that allows us to do that. So first we're going to have our select statement, and we're going to select customer ID, first name, and amount. And this is going to match up with the fields that we see in our resulting output. So basically what we want to see. And right here we have customers indicating that the customer ID field comes from the customers table, first name indicating that first name field comes from the customers table, and the amount field which indicates the amount field, and we have orders right here, which indicates the amount field comes from the orders table. So first we have the name of the table, and then we have a dot, and then we have the name of the field. Next we have from, and this is where things get interesting. So we're going to say customers inner join orders for both the tables that we're going to be accessing on customers.customerID equals customer. So basically the idea is that we're going to get this information for the relevant rows where the customer ID, for example right here, is equal to where a value in the customer ID field is equal to some value in the customer field right here. And correspondingly, the same applies right here where we have a value in the customer ID field that matches a value in the customer field. So right here is really where we get to see, or we get to decide from where we're going to get these values right up here. Now, one thing to keep in mind right here is, so basically we just aggregated information where based on where customers.customerID equals orders.customer. And when we have this on command right here, that's basically telling us how we're going to connect both tables, by what criteria we're going to connect both tables. So basically what fields are matching each other. But we can also add additional criteria to this. So what we could say, for example, is we could say where orders.amount is less than 600. And so that would actually eliminate this column or this row right here. And that's just something to keep in mind as we look at our next example, which is actually from an IB exam, but it's still a great way to illustrate how joins work. So right here it says a table has been split into two tables following the rules of normalization. The resulting two tables are shown with the primary key underlined. So we have Lori with truck ID as a primary key, truck make, energy source, driver, and telephone. For those Americans out there, Lori just means truck. And then we have trailer, which is what the truck is going to be dragging. And that has a primary key of trailer ID, trailer space, coupled from, coupled to, and truck ID, which is going to be like a foreign key. Now it says identify the steps to create a query to find the names and telephone numbers of the drivers who drive lorries that have more than 60 cubic meters of trailer space. So for names and telephone numbers of drivers, we can go right here to driver and tel. To find trailer space, we could go right here to trailer. So this is a case where we'd use joins because we're essentially utilizing information from two tables. We may not be outputting information from two tables, but we're still utilizing it. And we do have a common field in between both of those, truck ID and lorry, and truck ID and trailer. So let's go ahead and write our query. So the information we want is the names and telephone numbers from the lorry table. So we can do select, and then we can do lorry. I'll make it capital, lorry dot driver, and lorry dot telephone. And we're gonna do from, and our join is going to be, so our join is gonna be lorry. So we're gonna have lorry, inner join, and trailer. Then we're going to have on, and here we need to provide the condition, or provide that Boolean statement that's going to tell us what fields are equal to each other. So basically how to decide what rows coincide with each other in both tables, and that's pretty easy actually. We can just say lorry. In this case, that's pretty easy. We can say like lorry dot truck ID equals trailer dot truck ID trailer dot truck ID, and then we still have a condition. So our condition is that we want the names, or we want the drivers and telephone numbers for those lorries that have more than 60 cubic meters of trailer space. And this is actually important because this is the reason why we're using a join, because we need to be able to take into account information from our trailer table to be able to decide what to output from the lorry table. And to accomplish that, we're going to use where, and we're going to say where where trailer dot trailer space is greater than 60. And that's pretty much it. So if you go to the mark scheme, select driver tel. Interestingly, actually, they didn't use the table name, which I really think they should have. So from lorry inner join, trailer, on trailer, the trailer ID, lorry the trailer ID. Okay, I think we're pretty good here. Anyways, that's a great example of how you use a join and kind of how you judge whether or not to use a join. So we've got another example right here. It says, identify the steps to create a query to find the names of customers whose account balance is greater than 300,000. So, okay, so right here we have accounts. We have an accounts table. We have a customers table. And on the accounts table, we have account number, customer ID, balance, and account type. On the customers table, we have customer ID, family name, zip code, and phone. So this is probably going to be our common field between the two, what we're going to do the join on. Next, okay, so basically what we want to do is we want to find the names of customers, and that name is going to come from the customers table. It's going to be family name, whose account balance is greater than 300,000. That balance is going to come from the accounts table. So what we really want is, so we're going to say select, and what we really want is the name, and that's coming from the customers table. So select customers dot family name from, and then we're going to have, did I actually forget the from in the previous example? No, I didn't. I got the from. And we're going to have from, okay, so accounts, inner join, and then we're going to inner join that with the customers on, and basically we have the two customer ID fields. So accounts dot customer ID equals, let's see, customers dot customer ID, and then our condition is going to be, so we're going to say where, and that's where this is going to, where whose accounts balance is greater than 300,000, and that comes from the accounts table. So you can say where accounts, sorry, it's got to be accounts right there. So I'm kind of mixing between uppercase and lowercase, but, and on the exam, you should just use whatever they have on the exam. In practice, it doesn't really matter though. So accounts dot balance is greater than 300,000. And that's it. Go to the mark scheme. All right, yeah, looks pretty good. Cool, all right. Interesting, it says select customers.family name and accounts balance. Right here it just says find the names of customers, so we don't really need the accounts balance, but so I think we're good to go. Okay, so what we're gonna do now is take a look at a few A-level examples that cover SQL-based questions in general. The first one here says the database tables are repeated here for reference. So you have bird type with a primary key of bird ID, bird scene with a primary key of scene ID, also with bird ID right here as another field. We have person with a person ID primary key, and we also have person ID on bird scene. So it says complete the SQL script to return the number of birds of each size seen by the person with the ID of J23. So the condition is seen by the person with the ID of J23, but we're specifically looking at the number of birds of each size seen. So seen is referring to bird seen. And we kind of have, it seems like we're going to have, like, if we're talking about number of birds, we're probably going to have a count somewhere. If we're talking about size, we're going to be talking about this size field right here. And so we're probably mainly going to be working with bird type and bird scene, especially since we don't really have a relationship between person and bird type. But anyways, so if we're returning the number of birds for each size, and there are presumably multiple birds with each size, that means we're probably going to be doing some grouping right here. So we'll have a group by somewhere. Now, knowing that, I just want to go to where. And if our condition is seen by the person with the ID of J_123, seen tells us we're working with the bird scene table. And right here it says from bird type, comma, which means we're not just going to be working with one table, but with two tables. And it's probably going to be bird underscore scene right here, and then bird scene dot person ID, which is the field right here. And we're going to have select bird type size. We also have bird type size right down here, and oftentimes if you have group by or order by, it's going to be at the end of the SQL query. So this is presumably going to be group by because we're going to be grouping data for sizes together. And if you have select bird type size, and we want to see the number of birds of each size, and we also have as number of birds here, this is probably going to be a count to count up IDs that match this size right here. And that's also going to get grouped right down here using group by. The last thing we have is bird type.bird ID. So I think right here, this is another condition. So the first condition was bird scene and bird ID, but we also probably want to make sure that the bird type, or that if we're going to get a size, if everything's based on the size, then whatever bird ID we see in bird scene matches up to a bird ID in bird type. Otherwise, it just wouldn't really make very much sense because we wouldn't have any size for which we can count the number of bird IDs, or which we can add, for whose count we can add 1 to. We can increment. So we're probably going to say bird scene right here, dot bird ID. And so this is actually a weird one because we did actually get aggregate information from both tables, from bird type and bird scene. And I think one thing to keep in mind is that we could have actually done this with an inner join. We just chose not to. So we either have the option to, for example, use an and right here. So this bird type dot bird ID equals bird scene at bird ID. This would have been an opportunity for us to use an inner join and to kind of build the query around that, but we chose not to. So it's kind of good to see this, so you kind of see an alternative to using an inner join. The group by still could have been done, probably would have been a similar structure, but just another way of writing a query to aggregate information essentially from two tables. And also, when you fill out these queries, you don't have to do everything in order. Sometimes it's almost easier not to, because it allows you to kind of work your way into the query and do things in a more, kind of figure things out in a more logical fashion. Cool. All right, next. Example data from the table rental are given. Complete the following data definitional language statement to define the table rental. Okay, so first we're going to create table rental. Got some fields here for house ID. Okay, that's just going to be, this is going to be varchar. It's just going to be some kind of string. So it's like, it's alphanumeric. We have monthly cost, and that's going to be a real because it's a decimal. And deposit paid boolean not null. Right here we have rental ID. Okay, so we haven't specified the primary key up here, so it's going to be something like that. I think we actually did this previously, but still good to go over again. And it says write a data manipulation language script to return the first name and last name of all customers who have not paid their deposit. So, okay, we're going to return a first name and last name. Okay, so one thing that, this actually came from a different question, but one thing we can assume is that we have another table called customers. And there is a first name, there's a customer ID field, and there's a first name and last name field. Now, I'm pretty sure that actually there was a earlier part of this question which I didn't mention, but we're going to answer this question based on this assumption. And what we can actually do, and basically what we want to do is we want to find which of these haven't paid their deposit. So where deposit paid equals no. So I'm going to output the first name and last name for those people. So we can do select, and then we're going to select from the customers table dot first name, and then customers dot last name. And then, okay, once you've done that, we're going to do from, and then I'm going to do, so the name of this table was rental. I'll do rental, inner join customers. I guess I'll put that in uppercase. The case isn't so important. On, and then we're going to say on rental dot customer ID equals customers dot customer ID, and then our condition is basically where deposit paid equals no, and that's pretty much it. Now again, I kind of made up this table. I'm pretty sure this was an earlier part of the problem, but this is the only thing that kind of makes sense. So basically we could use a join for this. And right here we actually don't have a join right here. We just say where select first name, last name from customer rental. And we instead of having a join, we just have this and then we have what would be the join condition. Right here it says we could have used an inner join as well. So we're all good. Now next it says the relational database astronomy is used to store data about telescopes, the companies that own the telescopes, and the photographs taken by telescopes. The database has 3 tables. So we have company, primary key of company ID, photograph, and I guess we have a photo ID and telescope ID, and these probably function as like a composite primary key. We have telescope, and we have a telescope ID as our primary key. We also have a company ID field right here. So you've got a company ID field that links us to the company. And on photograph, we do have a telescope ID field that does link us to this telescope right here. Okay, so for A, it says a suitable field for the primary key. So basically what we need to do is we need to go in here and we need to figure out different information about each of these tables. And so here it says a suitable field for the primary key in company. And that's obviously going to be company ID. It says a candidate key in telescope. And it didn't ask for the primary key, which makes me think and candidate keys are both primary and alternative keys or secondary keys that can also be used as primary keys. So if it's not going to be directly the primary key, I would imagine that in telescope right here, company ID would also be another unique value. Actually, company ID is going to be more of a foreign key. Serial number would be another unique value, right? So, because that's presumably something that's going to be different for every record and which matches each telescope. So both logically and practically, it makes sense to be an alternate key. So something that would also be a candidate key. So we could say serial number, although telescope ID should also be correct, because candidate keys are both primary keys and any secondary or alternate keys. And the degree of relationship between telescope and photograph. So presumably for every telescope, we have many photographs, because we have telescope ID here as well. So I would say it's going to be like a one-to-many relationship. Cool. Okay. So a database management system has several features. Identify the feature that describes the relationship between data and its structure. That's going to be what's called a logical schema. We talked about logical and illogical schemas earlier, and yeah, that's going to describe a relationship between the data and its structure. It's basically how data is logically stored in the structure of a database, which is also called a schema. Next, complete the SQL script to return the total number of telescopes owned by the company whose ID begins with HW. All right, so whose ID begins with HW? All right, so total number of telescopes by the company whose ID begins with HW. Okay, so we're looking for company ID. We do have a company ID field on telescope. So right here, our condition is company ID, like, I would say like HW. We could just do something like this. And this means that we can have either one or no characters on either side. Either no characters or one or more characters. So we could either have some characters or no characters at all, either one on either side. And we want to select, what do we want to select? Just return the total number of telescopes. So owned by the specific company. Okay, so we're going to do count. Then we're going to count the number of telescope IDs. Just counting the number of telescopes that match this criteria. And it looks like we're good to go. Here we only had a percentage sign and one sign, but I think any of them should work. Like either one should work. Actually, no, I guess right here we strictly don't want any characters on this side. So actually, yeah, it should just be HW like that. We don't even want to have the option of having other characters, because if we have a percentage sign, we have the option of having other characters at the beginning or before HW, but we don't want that option. So I think it's better just to have HW and then the percentage sign, because we want to start with HW and then after that we don't care what happens. So little mistake, but it's all good. Okay, next, write the structured query language script to add a new record in the table tree to store the following data. Okay, so, all right, we have these attributes, we have these values. We want to insert this record into a table called tree. So we're going to say insert into, because that's how we insert into a new record, tree. And then we're going to have our attributes, tree ID, scientific name, and then we're going to have the keyword values. And then we're going to have the values that match each of those attributes for this particular record. So we'll have low _1276 for tree ID, salix _alba for scientific name, max height, 30 for max height, and true for fast growing. Okay, so for the last question, state what is meant by a candidate key in a relational database. So if we just go over to our mark scheme, it's an attribute that could be a primary key. That brings us to the end of this video. I just have some channel updates to close out the video. Basically, with regards to the theory content, paper 1, that's the thing I'm going to continue working through. The paper 3 study guide has been released with all the slides, and the paper 1 study guide is on the way. I'll actually probably release it before I finish working through all the videos for paper 1. So as far as programming, paper 2 course is in the works. I think probably what I'm going to do is I'm going to release it on my channel only for members. So you'd have to pay a subscription for about like $3.99 a month, and then you get access to all of the paper 2, like a bunch of paper 2 solved problems and maybe some explanations. But that's basically how that's going to work. However, I do want to finish the theory first. And finally, study break series. This is a series that's more of just like kind of vlogs. This will probably also be something for members only. I haven't really decided yet, but basically that's it. Anyways, if you enjoyed this video and want to see more like it, please consider liking the video and subscribing to the channel. Have a nice day.